Welcome everyone to the 2DCC webinar series. Today we have Dr. Vikram Deshpande from the University of Utah. He got his PhD from Caltech and he did a postdoc at Columbia University. And now he's a faculty member in the Department of Physics and Astronomy. Dr. Deshpande, please go ahead.
Yeah, thanks, Kevin. Thank you for that introduction, and thank you for the 2DCC Center for the invitation and for this opportunity to talk about some of the work that we're doing. So I'm over at the University of Utah, and you can probably see us out here. So this is our campus. We are by the Wasatch Range of the Rocky Mountains over in Salt Lake City. And yeah, so I'm going to talk today about some of the work that we've been doing on mechanically perturbing topological materials. But as I indicated in my abstract, my talk today is actually going to be a little more broad. I'm going to actually start out by introducing topological materials through our own work in this area, and that is specifically in the context of 3D topological insulators, where I'll start by introducing two mechanisms of gap opening, namely a hybridization gap and a magnetization induced exchange gap. And then I'll use those two topics as a way to essentially get into the main focus of today's talk, which is basically the mechanical measurements, and they will basically be applied to two different systems. And these are essentially the intrinsic magnetic TIs and an twisted bilayer graphene, which is another system that shows topological physics. Okay, great. So before I do all of that, let me acknowledge all of the people that did the work that I'm going to talk about. So most of the work that I will talk about today was done either by my former graduate student, Sukong Chong, who is now a postdoc at UCLA, or a couple of more recent grads, Shuan and Chuan Kun. Okay, and a lot of the work that I will talk about has been funded by this NSF tax award from 3 years back. All right, so a good place to start a talk on topological materials is basically the quantum Hall effect, right? So this is the celebrated effect where, back in the 80s, researchers took two-dimensional electron gases and applied perpendicular magnetic fields, and they found that instead of a straight line, as they would expect for the Hall resistance as a function of the magnetic field, they found a series of steps. And this is, of course, then led to a whole slew of other topological effects. And so, for example, in 2 dimensions, you have not only the quantum Hall effect that I just talked about, but also the quantum spin Hall effect, where essentially you have, spin helical edges that essentially circulate around the sample, a 2-dimensional sample, or the quantum anomalous Hall effect, where you basically have spin polarized edges instead of spin helical edges, right? And then in 3 dimensions, you have a whole slew of different complex topological materials, and both of these include a lot of excellent work that has been done or is being done at Penn State as well. Okay. More recently, for lack of a better term, we also have what are called multifunctional topological materials. And the idea here is that these are materials that have multiple ground states in the same material, and examples here include the magnetic topological insulators that I will talk about later, or moire materials such as twisted bilayer graphene, which again I will talk about later. Okay, so and finally a slide for why we should care about topological materials. I'm probably preaching to the choir here, right? But just for completeness, these are new phases and new ways of thinking about and classifying matter, and of course there are a lot of novel applications in the context of, for example, electronics, where you have these quantized 2D states that might be that basically host dissipationless transport, and that might be useful for electronics. You have the quantum spin Hall effect, for example, that has spin momentum locking, and that is basically particularly useful for spintronics. And of course, you have a whole bunch of materials that might be useful for topological quantum computing. Right. Okay. Yeah. So with that introduction, let me actually then get started with our own work, and I'm going to start particularly by talking about how we got started in this area, which was with 3D topological insulators. So these are, of course, the prototypical 3D topological state of matter. They were predicted and observed for the first time about 15 years back. And the general idea is that these are bulk materials that have an inverted gap in the bulk and protected, conducting Dirac-like surfaces. Right, and typical examples are bismuth telluride and bismuth selenide, and so while these are materials that are actually commercially used for entirely different reasons, for making thermoelectric coolers, for example, when people looked at their surfaces with surface techniques like ARPES, they found these really nice looking Dirac cones, and this was in the late 2000s. Right. Okay. So when other people, who do transport measurements actually try to look at these materials, they were, not as successful. They basically were only able to see indications of these surface Dirac states and only indications of surface transport. And that was because there was a big problem here, which was that the bulk of these materials was not actually insulating. It was actually the Fermi level was doped into one of the bands, and so a lot more work had to be done to get these materials to become more bulk insulating, right? And so in the mid 2010s, this was done by a few different groups, and I'm showing here the work of the Purdue group, for example, which came up with this quaternary compound, BISBTESE2, or BSTS for short, where they were able to obtain clean bulk insulating material and high quality surfaces. And upon applying a large magnetic field, so for example, they applied here 31 Tesla, they were able to get a quantum Hall effect of the surfaces. Okay, so this is about the time that we got started in this field, and so we essentially implemented our own growth of BSTS together with my crystal grower collaborator Taylor Sparks, who's my colleague at the University of Utah. And so so basically the thing that I want you to take out of this slide is basically that so if I look at this plot here of the ratio of the surface to the total conductance, so below about 100 Kelvin or so, you are essentially dominated by the surface conductance, right? And then the surface mobilities are also reasonable enough, a few thousandths, that you can then start to think about doing more interesting stuff. Okay, so what is it that we did with these materials? We basically made van der Waals heterostructures, which is combining these 3D materials with 2D materials, namely hexagonal boron nitride, which was a dielectric, and graphite, which was a gate. And then applying, for example, a voltage on the gate, you can essentially tune the chemical potential of, in this case, the top surface. And as you can see here, the longitudinal resistance essentially goes through a peak, indicating that you are going through the Dirac point of the surface. Okay, so you can do more. You can essentially, in a magnetic field, essentially get these Landau level fan diagrams, extract quantities like Berry's phase, for example. And because you have two surfaces, you can essentially implement two dielectrics and two gates and get these color plots that are essentially the longitudinal resistance in this case as a function of two gates. And where it peaks here in the middle is basically your global charge neutrality of your device. Okay, so now applying moderate amounts of magnetic fields, we can essentially get this particular plot to quantize. And so I'm plotting here now the longitudinal conductivity and the Hall conductivity of the sample as a function of the top gate and the bottom gate. And you can see here a series of plateau-like features, and they're plateaus in integers, even though each Dirac surface of this material is a half-integer quantum Hall effect, and that's because essentially the two surfaces are fused on the sides, and essentially what you're measuring here is a sum of these two half-integer quantum Hall effects, which basically ends up becoming an integer. Okay, so all right, so this is now a fairly thick sample. This is essentially a sample that is a couple of 100 nanometers thick. So you can now start to think about what happens when you start making these samples thin. And so one of the things that happens is basically that you start to hybridize the Dirac cones on the top and bottom surfaces, and you start to open up a gap. Okay, and so this gap, it turns out, may be interesting to study, because perhaps there are some interesting topological phase transitions that are associated with this gap. Okay, so, and there is also another mechanism of opening a gap, which is essentially by putting a magnet, a ferromagnetic insulator on one of these surfaces, and that's also something that I will address. Okay, so yeah, so we started making these samples thinner. And the first thing that we observed was that the surfaces started to couple, they started to talk to each other. So for example, this checkerboard that I showed you earlier, and this is now a checkerboard of the longitudinal and the Hall resistance, the conductances as a function of the two gates, essentially starts to warp as the material is made thinner. So this is now first a sample of close to 100 nanometers. As it starts to become thinner, the features start to warp, and as you make it thinner, the features start to warp some more, and finally at about 10 nanometers or even earlier, you can start to see that the charge neutrality opens up a small gap. Okay, so it's interesting to then figure out what is the nature of this gap. And although this is actually a gap at high magnetic fields, we can also start to make the samples further thinner and start to see these gaps appear also at zero magnetic field. All right, so there are, it turns out, some very interesting topological phase transitions that can happen essentially in this regime, the ultra thin limit of the topological insulator. And I have categorized these transitions as a function of thickness, magnetic field, and electric field. Okay. So more carefully, you have the following theoretical framework. So I am basically showing the same sort of a picture essentially now. So this is my parameter space. I have thickness on one axis, magnetic field on one axis, and an perpendicular electric field on the other axis. And you can basically see two different colors on this plot. And those two colors are corresponding to now two types of of two-dimensional gaps. So either a gap that is a normal gap or a gap that is an inverted gap, which is essentially supposed to be a quantum spin Hall effect. Okay, so this was an early prediction that was made back in 2010 for the case of bismuth selenide and bismuth telluride, and this is our theory here for the case of BSTS. But something like this has not been has not been seen so far, right? And so we started then to look at thinner samples and see what it can what it can show us, and so we essentially took samples down from 10 nanometers all the way down to 1 nanometer and studied gaps in these samples using 3 different transport-based measurements. So one of them was basically a thermal activation. The second one was a DIDV, and the third one was a measurement of quantum capacitance, right? And all of these 3 measurements, along with DFT calculations, show us that the gaps in the sample are increasing exponentially as the thickness reduces. Okay, so but our theoretical framework had shown us that there are two types of gaps, right? And so is it possible to see this in samples of adjacent thickness? And therefore, we considered, for example, samples that are 10 nanometers and 9 nanometers. And what we found, for example, was that, as we cooled these samples down, the 9 nanometer samples shot up in longitudinal resistance, whereas the 10 nanometer sample kind of saturated. And in fact, if you take the difference of the 10 nanometer and the 9 nanometer sample, it looks like basically the resistance, the difference of the two samples saturates exactly at h/2e squared. Okay. So you can again look at the two samples as a function of gate voltage. And you can see that the 9 nanometer sample, again, is shooting up, whereas the 10 nanometer sample is saturating as a function of gate voltage. And this is on a log plot. If I show the same data on a linear plot, you can actually see the saturation a lot more clearly. And so this is indicating that, there is basically an evidence of some sort of non-trivial topological behavior going on in this two-dimensional limit, and essentially just showing an indication of the quantum spin Hall effect in these hybridized 3D TIs for the first time. Okay, but we have two more parameter spaces to look at, namely the magnetic field and the electric field. And so we consider now the magnetic field response, the perpendicular magnetic field response of 9 nanometer and 10 nanometer samples, and the 9 nanometer trivial sample, for example, shows its gap, increasing monotonically to form a quantum Hall effect at high magnetic fields, whereas the non-trivial sample, the quantum spin Hall sample that I just talked about, essentially shows a crossing of the gap. So essentially a gap closing and a reopening at higher fields, again, evolving essentially in some sense from the quantum spin Hall to the quantum Hall effect. Okay, so this is the second evidence that there is a quantum spin Hall effect that is appearing in these samples. And then finally, we can use a perpendicular electric field to take a trivial sample, which is the 9 nanometer sample, and drive it towards the quantum spin Hall effect. And therefore, we're basically showing here that there are three parameters used overall: thickness, magnetic field, and electric field, to either realize or tune the quantum spin Hall state. And this is a work that appeared in Nature Communications a little while back. And in some sense, this also marks the entry of the fourth material system to show the quantum spin Hall effect. Okay, all right. So that was our, my introduction for essentially how Dirac cones on surfaces can hybridize to open up a gap. We can also, like I said, think of a gap opening mechanism by putting a 2D, ferromagnet, particularly a magnetic insulator. And in 2018, we tried doing this essentially with the 2D ferromagnetic insulator, chromium germanium telluride, and this was not very successful. We essentially saw features that were associated with essentially disorder at the interface of the magnet and the 3D TI. More recently, we worked with our collaborators at Cornell, Dan Ralph's group, and they have actually been able to make samples using our material that look like they have a lot cleaner interfaces, and they have shown recently that they can realize a gate tunable anomalous Hall effect in this type of a device. Okay, so yeah, so we have since then moved on into doing more mechanical measurements. And the idea is that these two-dimensional materials also have a mechanical degree of freedom that can possibly be used for, for either elucidating interesting physics or for changing the behavior of the materials. And we are also motivated here by our own previous work. So we have experience in doing various types of nanomechanical measurements, particularly in the context of graphene over the last decade. And we've tried to apply these sorts of techniques and experience into newer or topological materials, for example. Okay, so yeah, so with that, I will essentially talk about now, taking the idea of a magnetization induced exchange gap and talking about these new materials called intrinsic magnetic topological insulators that are, you might think of them as naturally occurring van der Waals heterostructures of TIs and ferromagnets. And and in our case, we are actually using a mechanical technique to study some properties of this material. Okay, so let me introduce this material quickly. So this is probably one that folks at Penn State have a fair amount of exposure to. Okay, so yeah, so MNBI2T or MBT for short is basically a system that consists of alternating layers of the magnetic layer MNTE and the topological layer bismuth telluride, and so folks have seen, for example, in RPS measurements, nice looking gap Dirac surface states, and other people have seen interesting magnetic transitions. So, for example, it appears that this material has 3 different magnetic phases as a function of magnetic field. So there is basically an antiferromagnetic phase at the lowest fields, a canted antiferromagnet at intermediate fields, and finally a ferromagnetic phase at very high fields. And then so we've essentially tried to think about if we can look at these different states in a different using a different technique. Okay, so more particularly, we are motivated by rich phase diagrams that look like this. So, for example, this is the phase diagram of various phases of this material as a function of pressure or strain, say, right? And so it looks like these phases are essentially being tuned by pressure or strain. And while we are not actually going to do that just yet, I'll talk about that in later in this talk. The question that we want to address right now is, can these sorts of magnetoelastic couplings, right? So basically the coupling of these various magnetic states to the lattice, can they be estimated in a nano device configuration? Okay, and our so our approach here is basically to use nano electromechanical resonators of this material, MBT. More specifically, the material is actually antimony doped MBT, which is supplied to us by 2DCC, by the group of Zhichang Mao, and Sam Lee is our collaborator who is helping us with this material. So let me actually briefly describe this geometry and these measurements. So the samples are basically drum resonators of MBT or MBST. So they're basically clamped on top of circular drums or circular holes that look like this. This is our circuit diagram for these measurements. So in short, we're basically measuring the RF transmission through the sample, and we're looking at this, for example, as a function of various parameters, and the RF transmission essentially peaks at frequencies that correspond to the mechanical resonance of these samples, as you can see, for example, in this transmission measurement as a function of gate voltage and frequency. Okay, so we use simple continuum mechanics models to model this behavior. So this is a continuum mechanics model that basically shows 2 different contributions to the overall energy. There is an elastic contribution and an electrostatic contribution. You then take 2 derivatives of this with respect to displacement and get the spring constant, which is basically then used to convert the spring constant into frequency and can be used to fit this data. Okay, so fits like this can give you, for example, things like built-in strain in the sample, and in this sample it was found that the built-in strain was about 1%, and this is the built-in strain due to sample fabrication. Okay, all right. So next, some quick transport characterization. So transport characterization done by us and our collaborators on these samples show that basically the same, three magnetic states are observed in transport as was seen by other groups, and so this is essentially fairly consistent with the literature. And so that is the point of this slide, which is to say that the transport signatures that we see in our MBT are fairly consistent with what other people see. Okay, and so now we can essentially take our mechanical samples and try to essentially look at whether they show any signatures of these states. Okay, so this is the data of the mechanical resonance as a function of magnetic field, and you can actually see that there are three different regimes here in the mechanical resonance, and these are actually corresponding to the magnetic fields at which there is, for example, so this is the center phase is the antiferromagnetic phase. At around 3 or so Tesla, there is a transition to the second phase, which is the canted antiferromagnetic phase. And at higher fields, there is another transition, which is now to the ferromagnetic phase, right? And so again, this is what these different phases look like. And so to confirm that we are indeed seeing these phases, we can also take a temperature dependence of this data. So this is data, I did not mention this, this was data taken at 1.5 Kelvin. And so taking the temperature dependence of this data, you can essentially see that as the temperature increases, the parameter space of these phases shrinks, and at about 25 Kelvin or so, which is also corresponding to the Néel temperature of this material, all of the transitions vanish, and therefore that's further evidence that these mechanical transitions are indeed corresponding to the magnetic transitions in the material. Okay, so using our data, we can also back out a phase diagram for this material. So this is now various different magnetic phases that can be seen as a function of temperature and as a function of magnetic field. Okay, so an interesting question to ask is, why are these magnetic transitions showing up in a mechanical measurement? Okay, so to answer that question, we have used the exchange magnetostriction model developed by the Cornell group for the case of a different material. Okay, so this exchange magnetostriction model basically has two terms. One term corresponding to essentially so there's two terms in the free energy, the magnetic free energy. So the first term is one that corresponds to the exchange, and the second term is one that corresponds to the anisotropy. Okay, and so we basically write out the free energies for the three different states. So the antiferromagnetic state, the canted state, and the ferromagnetic state. And to that we add basically the elastic energy and the electrostatic energy as before, and we again minimize this free energy and we connect it with the frequencies of the spring constants, as I mentioned earlier. And what that does is that basically gives us an estimate of precisely the magnetoelastic couplings that we were looking for, right? So basically it gives us an estimate of dj d epsilon, which is basically a measure of how exchange changes as a function of strain, and dk d epsilon, which is basically a measure of how anisotropy changes as a function of strain, and we can basically extract quantities, numbers for these quantities that are that look close enough to ones that our theory collaborator has obtained using DFT calculations. And the second byproduct of this analysis is that we can also, for example, estimate the magnetization of this material in this nano device configuration. Okay, so this is a work that has undergone one set of reviews in nano letters and is awaiting revision. Okay, so all right, so that was the second part of my talk. I am now going to move on to the story that I started out with, which was the hybridization gap story, which was basically the hybridization of the two Dirac cones of top and bottom surfaces. And we've actually continued this story in the context of a different material, and that material is twisted bilayer graphene. So you might imagine that, a similar type of hybridization can also occur in graphene, because indeed graphene also has Dirac cones, and when you put two graphenes on top of each other, these Dirac cones will hybridize. But more interestingly, there is a twist degree of freedom in twisted bilayer graphene, which makes things a lot more interesting, right? And then these are celebrated results now, that there is a specific angle called the magic angle, at which the bands go from being linear Dirac-like to being more or less flat, and then all hell breaks loose, right? You have various different states that appear. So you have superconductors, you have correlated insulating states. Other people have seen various magnetic states and anomalous Hall effects, and even quantized anomalous Hall effects in this material. And so it is indeed a very rich system. It is also thought, that more recently, for example, as mentioned by this recent review article in Nature, that built-in strain during sample fabrication might actually play some role in this physics, right? So there is essentially a need for controllable measurements that essentially tune or change the built-in strain in these experiments. And so that is the route that we have taken. Okay, so let me just quickly mention a couple of other transport-based measurements that have tried to look at strain as a controllable parameter. So there was work last year from Switzerland that basically tried to uniaxially strain. So these were graphene samples, and they basically found that there was a scalar potential that was arising in these samples. Other work, this was work out of Illinois that basically created a strain superlattice by essentially arraying, graphene on arrays of nanoparticles. And I'm only mentioning, two out of possibly more transport-based studies using strain as a controllable parameter. In our case, the approach that we have taken is to basically fabricate samples on flexible substrates. Okay, and so the way we do this is we basically fabricate these samples, on polyamide instead of on solid silicon, and then we clamp them essentially on a circular, around a circular, in a circular sample holder, and then we drive a tip through the sample and study these samples as we apply strain to them. Okay, so the device fabrication is actually, quite a lot like what the rest of the community does. So I'm not going to focus too much time on this. All right, so let's talk about our strain measurements. So first we calibrate our strain by essentially looking at how pre-patterned alignment marks essentially move as a function of the Z displacement, and that gives us a measure of what is the strain in our substrates. Okay. Another thing that you can do to calibrate the samples is to basically use simpler samples. And so we use, for example, monolayer graphene. And so this is monolayer graphene in the quantum Hall regime. And the thing that we find is that essentially as we increase the displacement, the Z displacement on the samples, the RxX minima, or basically the quantum Hall plateaus, if you will, are shrinking closer to charge neutrality. And we see about a 10% shift in the VG minima for our largest strains. Okay, so how do we explain this? Well, so basically, the gate does two things to the samples. It basically changes the charge density in the samples, and it changes the chemical potential of the samples, right? And when you apply strain, both of these mechanisms can get affected. Okay, so strain affects the first term through purely the compression of the dielectric, thereby increasing the geometric capacitance of the samples. And secondly, it can basically affect the second term by strain essentially stretches out the bonds in the sample, and thereby reduces the hopping parameter, which then reduces the Fermi the Fermi velocity. Okay, and so this is the second mechanism in which strain can affect these samples, and so plotting essentially fitting our data to this model, we find that it's the second mechanism that dominates by almost an order of magnitude over the first one. And so basically the general idea is that as you strain these samples, your Dirac-like bands are starting to get slightly flat, right? And so we find that there is about about a 2% change in Fermi velocity for every single percent of strain. And we have seen up to a few percent change, up to 8% change in Fermi velocity in our samples. All right. Okay. Great. Okay. So yeah, before moving on to twisted bilayer graphene, there is one more thing that I need to introduce, which is basically that the magnetic field response of twisted bilayer graphene is dominated by what's known as Hofstadter spectrum, and the general idea here is that because there is a natural length scale that arises in these Moiré superlattices, which is the size of the Moiré unit cell, there is basically an interplay between the Moiré unit cell and the magnetic length that gives rise to this fractal structure. For our purposes, we only care about these vertical lines, which are actually horizontal lines, because we are plotting our data as a function of density tuned by gate voltage on the x-axis and flux tuned by the magnetic field on the y-axis. So you have these horizontal lines that are called Zach bands that appear whenever you have a rational amount of of a flux quantum going through a unit cell of the Moiré superlattice. Okay. All right. So yeah. So let's look at our data. So this is a twisted bilayer graphene device at 0.56 degrees. So this is the Hofstadter spectrum of this device. And then you can already start to see these horizontal like features. And so yeah, I've kind of drawn some helpful guides to the eye here. And so this is at zero displacement. And as I start to apply my Z displacement, I find that these features move down. Okay, so we find that so for example, in this sample, the features move down by about 8%. And that basically suggests that that the Moiré unit cell has basically expanded in size because of the strain by about 8%, which basically means that there is a 3% increase in the lattice constant of the sample. Okay, so we've seen this in several different samples. So I show here two more samples where on my horizontal features in the Hofstadter spectrum shift down. So this is a sample at 0.86 degrees. Here's another sample at 1.65 degrees, and both of them, all of them are indicating the same thing, that as you apply the Z displacement, the graphene itself is being is being stretched out, which is a fairly natural thing to expect. And then at zero field also we see the effects. So basically our mini bands at zero field essentially also start to shrink towards charge neutrality, just as the Landau levels of graphene, of singular graphene, seem to shrink towards charge neutrality. So the picture here is quite the same as the one that we found in singular graphene, which is that bands are essentially starting to become more flat as strain is being applied. Okay, so that's kind of where I would like to stop my recorded part. Let me just summarize and say that, okay, so I've shown, essentially I started out by talking about our work on 3D topological insulators, and I talked about two different gap opening mechanisms, essentially. So one being the surface hybridization gap, where Dirac cones of top and bottom surfaces essentially hybridize and lead to a quantum spin Hall effect. There is also the magnetization-induced exchange gap that our collaborators have used to get a gate-tunable anomalous Hall effect. And then I talked about how these two topics, naturally led into two more topics, namely the topic of the magnetic TIs, which was, in some sense, a naturally occurring heterostructure between ferromagnets and TIs. And here we used a nanomechanical technique to detect magnetoelastic couplings. And then secondly, I talked about the extension of our intersurface hybridization work. And we applied that to the context of graphene, and we showed here, for example, strain tuning of graphene Landau levels and the Hofstadter spectrum, and the general idea being that there is essentially a strain-induced band flattening that is appearing in these samples. Okay, so I would like to thank again, my students, mainly Sukong Chong, who did the nice work that I showed on 3D TIs, Xuan, who did the work on magnetic TIs, and Chuan Kun, who did the work on tested bilayer graphene. My collaborators for this work were my colleagues Feng Liu and Taylor Sparks at the University of Utah, and Zhichang Mao's group at Penn State, among others. And right, so I guess I will stop there.